I'd now like to talk about what happens if we already have a group on the ring, and we're going to see what happens when we attempt a second substitution. Now, the second substitution that occurs will occur in accordance with whatever is already connected to the ring, and we have to look at the nature of what's connected to the ring. We have two kinds of X groups that could be initially connected to the ring. We can have an activating group, or we can have a deactivating group. If it's X is an activating group, then what's going to happen is we're going to get two products. We're going to get an ortho product and a para product. If X is a deactivating group, then we're going to end up with a meta product. Now, the kinds of groups that we're talking about as activating groups will be these kinds of groups here: NH2, NHR, NR2, OH, OR, alkyl, or RCO, NH. And what we're looking at here are groups that are considered to be electron donating. These groups here, the C double bond OR, C double bond OOH, C double bond OOR, C double bond ONH2, SO3H, which is actually S with two double bond O's on it, NO2, C triple bond N, and NR3 plus are all considered to be deactivating groups. And those groups will tend to suck electrons out of the ring. Alright, so that's what I've got here. The top reactions have an activating group that pushes electron density into the ring. The bottom reactions have a deactivating group and they pull electron density out of the ring. Alright, so let's look at how activating and deactivating groups work. So activating groups, as I said, will push electrons into the ring, and they will do so because they have a lone pair, or they can do so by hyperconjugation. So what's going on is we've got electrons on the nitrogen, and those can actually push into the ring, and you'll notice that the partial charge on the end is considered to be a delta negative. Therefore, we're adding electron density into the ring by having this group attached to the ring. This works when you've got an N, but with all single bonds attached to the ring, and here an O with all single bonds attached to the ring will also work. Again, we've got the lone pairs on the oxygen, and we've got the partial negative charge that's adding electron density to this ring. The way that it works with the alkyl groups, they're not incredibly activating, but they are better than hydrogen certainly, and I'll just show you how the hyperconjugation works with that. So if you've got an aromatic ring, and you've got an alkyl group attached to it, what can happen is the electrons in the CH bond can be donated to the ring, at least a little bit, through hyperconjugation. We talked about that earlier. It's the same kind of thing that stabilizes C pluses as well. But the addition of those electrons to the ring, or at least a very weak addition of electrons to the ring, will cause an activating effect, and electron density ends up being donated into the ring. Now, the deactivating groups work this way. What they do is they actually suck electron density out of the ring. That's because the atom directly attached to the ring is now delta plus. So the electrons in the ring are attracted to the positive charge. So you can see that the delta plus here is on this C, and the reason this C is delta plus is because the oxygen here it's connected to is delta minus. That's a very polar bond. We have a delta plus on the C, a delta minus on the oxygen. With the nitro group, we already have a positive charge on the N because of the way that the nitro group is drawn. So the electrons again are sucked out towards the N plus. When we have an N with 4 bonds on it, it's going to be positively charged, and again the electrons will be attracted to the positive charge. The difference between this one and the one above here is the nitrogen only has 3 bonds and therefore has a lone pair of electrons on it. Once you add that 4th bond, that lone pair of electrons is gone and nitrogen is now positively charged. With the C triple bond N, the electrons are attracted to this C with the delta plus, so this is also considered to be deactivating. And with the S double bond O, the electrons are also attracted to the partially positively charged S. So in summary, here's what we're looking at. We're always looking at the atom directly attached to the aromatic ring. And if that atom has a delta minus or lone pairs of electrons, it will be considered to be activating. If the atom directly attached to the aromatic ring has a delta plus, then it will be considered to be deactivating. So you can see that that's what happens is the plus sucks electrons out of the ring while the minus pushes electrons into the ring. As a general rule, if you look at the deactivating groups, you can see most of them have a multiple bond. So you've got C double bonded to oxygen, N double bonded to O, C triple bonded to N, and S double bonded to O. The only exception here is the N with the positive charge, which we can see is clearly positive anyway, so there's no secret that that's going to be a deactivating group. So if you're looking for deactivating groups, I tend just to look for atoms that are multiply bonded, but we have to concentrate on the atom that's directly attached to the aromatic ring. Otherwise, none of this matters. Alright, so let's look at how these work and how they actually end up giving the products that we discussed earlier. As I said, activating groups give strictly ortho and para products, while deactivating groups give strictly meta products. Let's see how that works. Alright, so we've got an activating group attached to the aromatic ring here, and the products are going to be ortho and para. We've got to figure out why that's going to happen. Alright, first of all, let me show you what happens when we attach an electrophile to the aromatic ring, and we're going to look at some of the resonance structures that are going to be possible. I'll show you this step by step in a separate diagram here. Alright, so we've got our group attached to the aromatic ring. And we're going to attach an electrophile to that. And we will put the electrophile purposefully in the ortho position to begin with. Now if we want this in the ortho position, then this is the double bond that's going to have to attack. If we wanted it in the meta position, we'd use this double bond. And if we wanted it in the para position, we could also use this double bond as well. Anyway, let's look at the ortho first. Now the pattern that I've been discussing is that the double bond will add to the electrophile. Don't forget there's already a hydrogen here. And when the double bond adds to the electrophile ends up attached to that carbon atom, and the positive charge will end up over here. And that's because we're taking two electrons from this bond and forming a bond between this C and this E. This carbon is now short an electron, so it becomes positively charged. Now this positive charge is actually capable of resonance, and it's capable of resonance with these two double bonds here. So let's have a look at how that happens. To draw that arrow a bit more clearly. There we go, that's better. So if we take two electrons out of this CC double bond and we form a new double bond here, that will have the effect of moving the positive charge down to here. So now we can see the positive charge can also be here on the ring. I can also move this double bond as well, and that's a resonance structure we're talking about here. This is another possible resonance structure. And then we can lose the H plus and we can form our ortho product. But the reason I wanted to show you this was so you can see how we get these three possible resonance structures. So just explaining the first one here. What we're doing is we're taking two electrons out of this CC bond and forming a new bond, a new double bond between these two carbon atoms. That will short this carbon and electron, which is what makes it positive charge. Also the same explanation here for this positive charge, but it's really important you keep the direction of the arrow in the correct way, so it always comes from the bond and goes to the new bond, and the positive charge will move 2 carbons down. It's always going to be the way the pattern goes. Alright, so that's how we get our ortho product. Alright, we can do something similar with these other ones as well. If we want to look at the para product and the meta product, we can do similar resonance structures. So I've shown you how to get those resonance structures. You do the same thing with the para and the meta as well. And in the case of the para, I reacted with this double bond, and that puts the electrophile down in the para position. And to get the meta, I reacted with this double bond, and that allowed me to get the electrophile in the meta position. Alright, so what's going on here? If this is an activating group, then it's already got a delta minus on the X. And if there's a delta minus on the X, that means if there's a resonance structure where the positive charge is directly below the delta minus, we're going to call that a favorable resonance structure. All these other resonance structures are neither favorable or non-favorable, but this one is definitely favorable because you've got a positive directly under a negative. So a situation where you've got a positive directly next to a negative is always going to be a good situation. And if we're starting out with a ortho arrangement, then this favorable resonance structure is possible. So that's why I put a square around it and label it favorable resonance structure. Now if we do the same thing with the electrophile being added to the para position, here's what happens. The positive charge can end up here, or it can end up here, or it can end up here. And again, you'll notice we have the possibility of having the positive charge directly under the delta minus. So that again leads to a favorable resonance structure. Now in the case of meta, you'll notice that the positive charge can never end up directly under the X. It can end up here, it can end up here, and it can end up down here, but it can never end up being under the X. So what we're saying there is that in the case of an activating group, we've got the possibility of favorable resonance structures only if the electrophile adds to the ortho or para positions of the aromatic ring. In the case of meta, we don't end up with any favorable resonance structures, so we don't end up seeing a meta product. If we take a look at the deactivating groups, here's what happens. We now have a delta plus on the X group. We end up with exactly the same resonance structures possible as we had with the activating group. But now, what was favorable in the past is now unfavorable. So a delta plus next to a plus is now going to be an unfavorable resonance structure. And when we have the ortho, we do get the possibility of having this unfavorable resonance structure. That's why I put a square around it, mark this as unfavorable. When we try and put the E plus in the para position, the same thing happens. Again, we end up with this nasty unfavorable resonance structure. Remember in the previous one, both of these resonance structures were favorable because the X group had a delta minus and could stabilize the positive charge. Now the X group is having the opposite effect. It is now destabilizing the positive charge and leading to the possibility of unfavorable resonance structures where there were favorable ones before. Now since ortho and para end up being unfavorable or giving unfavorable resonance structures, those won't occur when we have a deactivating group. Instead, what's going to happen is that we're going to get the meta product because no unfavorable resonance structure will occur in that instance. So in summary, what I'm saying is that if you have an activating group, you'll just get ortho and para products because you have favorable resonance structures. In the case of deactivating, you do not get ortho and para because those would lead to unfavorable resonance structures. So by default, it will go via the meta route, and you'll only end up getting meta products because that won't ever leave you with a situation where the positive charge is directly under the X group. It can't be in meta because the positive charge ends up here, here, and here, and never ends up under the X group.